we shall begin, and oops, all right, and okay, and so we left off on Wednesday. We left off. We said we can take the derivative of a function with respect to a vector, right? So. Okay, and when we do that, the result, we call that the gradient. Okay, this is the gradient, and so, you know, you've got f of some vector w, and then the gradient of f is going to basically be the derivative of the function with respect to the vector, and that is itself is going to be another vector with partials for each component. And so we can kind of get used to the idea of taking derivatives. Derivatives in matrix notation. All right, and so here are some useful identities. So if we have a function, then the corresponding gradient would be something like this. So if we have w transpose x, then the derivative of that with respect to w, so I should say will be just x. Okay, and if you have, on the other hand, x transpose w, you also get x. If you have w transpose w, then you will get 2w. W transpose some matrix C. Okay. And this you get 2 times the matrix times the vector. How do I do this? I can't. All right. I don't know. I'll have to go in and where did it go? Here it is. Okay. Well, I'll have to save it as the wrong thing and rename them later. Okay. That's fine. Okay, so that's what we have, and okay, is that good? No? Oh, it's okay. Oh, here we go. Oh, look, you can decide to, now I can rename it. That's what I wanted to do. All right, so this is going to be week 1, Friday. Why is this so hard? Okay. Okay, so we talked about taking the gradient. Okay, and then so let's go back to least squares regression. And we said we've got some kind of loss function, right? And here the loss function is defined as the kind of the mean squared residual. And let me just write that out so that the loss function will be defined as 1 over capital N, the sum from n equal 1 to big N of T sub n minus W transpose xn squared. And we said this can be rewritten as, in matrix notation, we said this could be T minus the matrix X times W transpose times T minus the matrix X W, right? And then we expanded this out, and we got kind of T transpose T minus 2W transpose X transpose T plus W transpose X transpose X W. Okay, so this is the loss function when we write it in matrix vector notation. And let's say we want to apply this concept of taking the gradient, right? Because what we're trying to do is we're trying to find the minimum of the function. So we want to find the minimum of the loss function. Okay, and the way we will do this is we will take the gradient of this, or the derivative of this function, and find where the gradient is equal to 0. Okay, so we will take the gradient and find where it equals 0. Okay, or in this case 0, 0. So we will say the gradient of L is going to be defined as kind of the derivative of L with respect to W, which will just be kind of the partial of L with respect to W0, and the partial of the loss function with respect to W1. Okay? Transpose. So that's what we want. Okay, and so we'll say this is our loss function, and we will work through this in matrix notation. Okay, so what we will get is the gradient with respect to W is going to be, so I will just go ahead and distribute the 1 over n on everything, and okay, so we've got 1 over n say this is just dw of 1 over n t transpose t minus 2 over n w transpose x transpose t plus 1 over n w transpose x transpose x w. Okay, and so if we say, what is this with the derivative taken against 0? This is, I mean, with respect to w, there's no w term in here, so this just becomes 0, right? Okay, and then if we say, okay, well, what is this with derivative with respect to w? We're going to get minus 2 over n x transpose t. And what is this? Okay, well, we'll just do one of these, okay? And we will say plus. So basically, this is like the WCW, right, from the previous identity. You know, what's the derivative of WCW? It's going to be 2CW. So this is going to become 2 over n x transpose x w. Is that okay? All right, and so this is our derivative, and we will just set this equal to 0 and solve for w. So we'll set this whole thing equal to 0. All right, and when I do that, I'm going to just add this term to the other side, and so now I have basically 2 over n x transpose x w is equal to 2 over n x transpose t. So far, so good? Okay, we'll eliminate the 2 over n's on each side. Okay, and then so on my next slide, we've got I got x transpose x w equal to x transpose t. And what we'll do is we will just we will get rid of this thing on this side, and so we'll multiply both sides by the inverse. X transpose. So you can't divide matrices, right? But you can multiply them by inverses. And so when you multiply a matrix by its inverse, it gives you 1. Or the identity matrix, I should say. Okay, and so on the left-hand side, I've got x transpose x inverse times x transpose x w. So this whole thing becomes the identity matrix. And on the right, I will have x transpose x inverse x transpose t. And that's what we get. We get w hat, our best estimate of w hat is going to be exactly this, x transpose x. I don't know if this looks familiar. X transpose x inverse x transpose t. Okay, so this is going to be our best estimate of the vector w. So if we want to minimize the loss function. This is the result that will give us where the loss function has a gradient equal to 0. And so this is the estimate of W that minimizes our loss function. All right, and the beauty of this is that because it is in matrix notation, is that even though we kind of did the example where W was a vector of length 2, this can now be generalized so that W can be a vector of length 10 or 100, you know? So with matrix notation, the same results will hold even when the vector W has a length much greater than 2. Okay, so we could have some more complex linear regression model, and the same results will hold. Yes, question. How do we know the inverse exists? That's a good question. I guess we kind of just assumed that it does. The inverse will exist as long as the columns in X are not linearly dependent, right? So yeah, I guess I kind of just waved my hands and said, we'll assume that it does exist. But yeah, I mean, in kind of a linear regression example, it probably won't be a problem unless your data is contrived in such a way. But I mean, if you have two predictors that are exactly the same, it does create a problem in trying to find coefficients to estimate, right? So if you have a set of, if some of your predictors are linearly dependent, it does produce problems in linear regression when trying to find coefficients. But other than that, we shouldn't run into a problem. But yeah, okay. These results okay? All right, so we'll just do a quick example. All right, and this is straight from the textbook. Okay, so this is example from the text. And let's say we've got 3 data points. 1, 4.8, 3, 11.3, and 5, 17.2. So we will put this into matrices. So my X matrix is going to be a 3 by 2 with the values 1, 3, and 5. And then my vector T is going to be the outputs 4.8, 11.3, 17.2. Okay, and so our estimates, kind of the best estimates for W are going to be X transpose X inverse X transpose T, and so this would look like X transpose would be 1, 1, 1, 1, 3, 5 times 1, 1, 1, 1, 3, 5, and if I do the math, I will get 3, 9, 9, and 35. Okay. And so, you know, there's different ways for finding, so here this is equal to x transpose x. And so if you have some matrix, here, on this side. Okay, so this is, you have some matrix A with elements A, B, C, and D. Then the inverse of A is going to be 1 over, and you do A times D minus B times C, kind of like the determinant, and then you kind of flip these terms around. D and A and negative B and negative C. This is just kind of one way to find the determinant, or not determinant, the inverse of a matrix. So if I apply that to our thing here, I would get 1 over 3 times 35 minus 9 times 9. And I would do 35, negative 9, and 3. Okay, and so when we do this, we end up getting x transpose x quantity inverse becomes, this whole thing is 105 minus 81, which is 24. So I get 1 over 24 times exactly this, 35 minus 9 and 3. I'll just kind of put that up a little bit. Okay, so x transpose x that, and if I multiply this by x transpose and then t, so we're going to go ahead and multiply this by x transpose, 1, 1, 1, 1, 3, 5, so I'll throw that in over there, and we will get 1 over 24, and doing this 35 minus 9 will give me 26, and then 35 minus 27 gives me 8, and then 35 minus 45 gives me minus 10, and then over on the lower hand I have negative 9 plus 3 is minus 6, negative 9 plus 9 is 0, and negative 9 plus 15 is 6. So I have that, and then so lastly I've got x transpose x inverse x transpose t. So I have 1 over 24 times all of this. .8, 11.3, 17.2, and what do we get? I'm going to go ahead and just cheat and take the answers that I wrote out earlier, and the values end up being 1.8 and 3.1. I mean, we would just go through and do matrix multiplication here, right? Okay, and this would be my values for W0 and W1. Okay, so therefore, if T hat is equal to W0 plus W1x, our estimates would be 1.8 plus 3.1. Okay, so, yeah, I mean, and we don't really do this by hand anymore these days, right? We just throw things at the computer and say, computer solve, and it does the work for us. Computationally, the hardest part is taking the inverse of a matrix It's real easy when you have a 2 by 2 matrix, but if you have something more complicated than that, it's kind of hard taking the inverse of a matrix. What's that? Yeah, so I would say you should know how to do an inverse of a 2 by 2 matrix, but I won't ask you for anything harder than that, okay? All right, is this good? So this was, we went straight for the answer because we know that W hat is X transpose X inverse X transpose T, right? So we know that this solution is what's going to minimize the function, the loss function. All right, let's take a step back and say, what if, for whatever reason, we couldn't figure out how to solve for where the gradient of the loss function equals 0, okay? So this is a possibility, right? We couldn't figure out where the gradient of f equals 0. And so what can we do? We still want to minimize the loss function. Or I should say the gradient of our loss function is equal to 0, okay? We still want to minimize function, okay? Well, we have a tool, basically an algorithm, that should help us find at least a local minimum, okay? We have a tool, and this is called gradient descent, okay? Or some might call it gradient ascent, or you might call it steepest. So here I'm talking about minimizing, so it's a descent, but for others it's a maximization. So it's the same thing, right? And some people might call it steepest ascent. Gradient descent, and this should help us find a local minimum or maximum, depending on your application. The problem with this is you won't know if it's a global minimum or maximum. If it's a quadratic, there's only one minimum, so the local is the max global. But on anything more complicated, which is pretty much everything else, it's hard, okay? But it's okay, it's still a useful tool. And so this is what we do. Okay, let me just give you kind of a one-dimensional case. So this is the idea for one dimension. Okay, so you have a function of one variable. And we will say our function looks, we'll just make a simple parabola, okay? Right here. Actually, we'll do a real function, which will be x minus 1 quantity squared, which is going to be x squared minus 2x plus 1, okay? And this function will look like this. Okay, so it's a parabola, and it crosses, or it touches at x equals 1. Okay, the idea here is that you just start at some point, okay? And you ask, what is the derivative at this point? Okay, and if we ask, what is the derivative at this location, it would tell us kind of the line that's tangent to it. Okay, so it kind of tells you in what direction is the function increasing, right? So we take some value. Value of x, and we find derivative of the function at x. Okay, maybe I'll call this x0. Okay, and that will tell us the how f changes when x changes, right? So it tells us, basically, and the key part is the direction that f changes, that f of x changes at that location. So, if at alright, so let's say at x sub 0 equals, let's say 2.5, then the derivative of f of x would be 2x minus 2 evaluated at 2.5 would be equal to 3. Right, so the slope of this tangent line right here would be 3, and it tells me that if x increases, then f increases 3 times faster than x. Okay. And so if we wanted to approach a minimum, we would go in the opposite direction. We would say, okay, increasing x will cause an increase of f. So if I want to decrease f, I would decrease x at this location. So at this location, if I want to decrease f, I would decrease x. Is that okay? Because my derivative here is positive. Over on this side, let's come over here, okay? And let's say I'm at this location over here. The tangent line goes like this. So we'll say at okay, so we'll say at x0 equals, let's say 0, then d dx would be 2x minus 2 at x equals 0. This is going to equal to negative 2. So what this tells me is that when over here, when x increases, f decreases. So to decrease f, we will increase x. Okay, so by taking the derivative, this will tell us in which direction we should move if we want to increase or decrease f, right? So if we take the derivative at x and the derivative is positive, if our goal is to minimize f, then we would move in the opposite direction. We would move to smaller values of x, okay? If we take the derivative at a certain point in the function and the derivative is negative at that point of x, and we want to decrease f, then we would increase x, okay? So that's kind of the idea that we have, and we just kind of generalize this to the multivariate case, all right? So if I can, so kind of from the one-dimensional case, okay, we learned if basically d dx is positive, to decrease we will decrease x, and if d dx is negative, to decrease f, we will increase x. Okay? So one way we can do this is we can just say the next value of x should be, we're going to just do x0 minus, and I will just write kind of like f prime of x0, okay? And it's, I'll say this times some constant lambda, where lambda is a positive constant. Okay? Because this will determine kind of the sign. So this will either be positive or negative, and if what we want to do is decrease, then we just kind of move in the opposite of whatever this sign is, right? So if this thing is positive, then the next value of x should be smaller than our current value, and if this thing is negative, then the next value of x will be greater than our current value of x. So that's what we do. Okay. Does this kind of make sense? All right. And one nice thing about this is that when the slope is very steep, we can kind of comfortably take a bigger step, and as we approach areas that get more and more and more shallow, our steps will get smaller and smaller and smaller. Okay? So this also scales, kind of scales with the slope. So that you know, areas where f is steep, we take big steps. Okay, and when f is shallow, steps. Okay. So this allows us to, we're able to find the form of the derivative. Maybe we couldn't figure out where the derivative is equal to 0, but by knowing the derivative, or in the multivariate case, the gradient, we can at least know in what direction should we be taking steps. Okay, so it's like we'll take a little step. Okay, so this was kind of the one-dimensional case, and all I'm going to basically do is just replace the derivative with the gradient, and that will be our multi-dimensional case, right? So in a multi-dimensional setting, we can do the same. We can use the gradient rather than the derivative. Okay, so we'll say we have some function f. And we'll say delta f is the gradient, which is going to be, a vector in n-dimensional space. Okay, and if we think about what a vector is, it's an arrow, right, in n-dimensional space, and so this is not just do we go positive or negative, but now it's an actual direction that tells us which way is the steepest ascent or descent here. Okay, so to minimize f is a vector in n-dimensional space. It tells us the direction that f changes at some location. And so to minimize f, we will take a step in the opposite direction. Okay, so we'll say if we begin at location x sub n, then our next location should be at time xn plus 1 should be our location xn, and we're going to take a step in the opposite direction of whatever our gradient is at location x sub n. Okay, so here again, lambda is a positive constant. And usually lambda is kind of a small value, like maybe 0.01, and that's just to make sure we take a small step, okay? Yes. You have a question? Yes, I'm sorry. How is lambda determined? That is a hard question, and I don't have a good answer for that. We often start with a small lambda, and then we'll see, and if it takes too long, then we bump it up, or maybe we start off with lambda, and then our thing acts crazy, then we decrease lambda. We don't. There's a little bit of a trial and guess here. I'll draw kind of an image of what is happening, and then we'll probably pick up here. Oh, I guess we'll. I won't see you guys until Wednesday. We have Martin Luther King holiday. So let's say we will have on Monday. Yeah. So let's say you've got this paraboloid. And so if we take a look at kind of the contour image from above will look, and let's see if I can. Something like this. Okay, and if we are at some location here, okay, if I draw, if I'm at a location, this the gradient at this point is going to be a vector that says this is how the paraboloid increases, right? So here I'm kind of at that location. If I'm at another location, perhaps on somewhere on the other side of the thing, you have kind of this. It shows where it goes, and generally, the gradient at some location is going to be a line that's perpendicular to the tangent line, okay? Or is perpendicular to the tangent line here. So let's just see here, and if I'm over here, it might say that that this is the spot. So if we are located right here on the parabola, then our next location, we will take this and this thing here. Let me just redraw this. This represents the gradient of f, and if this is x0, then x1 is, we're going to just take a tiny step in the opposite direction. This is going to be, this little thing is lambda times the gradient of f at x0, okay? And our next thing will be right here. And when we do this, what we'll end up getting is kind of a bunch of little arrows that slowly descend until we get to the middle here. Okay, and if we did the same thing on the other side, you know, wherever we start, we would just take kind of little steps, and we would end up converging to where the lowest point is. So at each iteration, we're just taking a little step down the hill. So it's basically just, you're giving someone instructions and they say, how do I get to the bottom of the hill? You're just saying, look around and see what's downhill and just take a step downhill, okay? If you keep taking steps downhill, you'll eventually get to the bottom. And that's what we're telling the thing to do.